Okay, my name is Wajahat Chima, and this is homework number 5, question number 2. So we're given that the function of x and y is equal to 1 over ax squared y, where x is greater than or equal to 1, and y is between 1 over x and x. So just to get an idea of how this looks graphically, I attempted to make a 3D graph. It looks sort of like this. When x or y becomes small, the value of f of x and y becomes increasingly large. That's because x and y are in the the denominator, and anything, if one is being subtracted by an extremely small number, it becomes larger and larger, so it progressively becomes bigger and bigger. So also in addition, I drew the graph for x. This is x right here. This is 1 over x, and y being in between will be in this region right here, and this is where it meets is 1, so this is going to be important, this graph right here. Alright, so starting off, then you do double integrals f of x y dy dx equals 1, from 1 to infinity, and from 1 over x to x, we can swap out this value for this, 1 over ax squared y dy dx, which is equal to 1 over infinity, negative 1 to infinity, 1 over ax squared. This is a constant, we just pulled it out. The derivative of 1 over y is just ln of y from x to 1 over x, so we get negative 1 to infinity ln of x minus ln 1 over x ax squared dx. And from there we go to here, from 1 to infinity ln x squared ax squared dx. If you remember anything about logarithmic functions, since x is to the second power, we can take out the 2. You can take out the a, put it on top here, since a is a constant, and then this equals 1 over infinity ln of x over x squared dx. And using integration by parts, we can figure this out, and we get negative ln of x plus 1 over x from 1 to infinity equals 1. And then just 2 over a, 0 to 0 minus negative 1, and that just equals 1, so a just equals 2, and this will be the a value right here, so it would just be 1 over 2x squared y. Alright, so now for the second part. So in order to find MDF, we have to integrate over bounds of y for f of x. So this is what it looks like, 1 over x over to x, 1 over 2y x squared dy, and this equals 1 over 2x squared. Again, these are constants. 1 over y is just ln of y, and then further on is ln of x minus ln 1 over x 2x squared. Again, using the logarithmic functions, the properties, we get 2 ln x 2x squared. 2's cancel out, so that just equals ln of x squared. Similarly, to find f of y, we integrate over these bounds here to infinity. 1 over 2y x squared dx equals 1 over 2y, constants again, negative 1 over x, that's the derivative of 1 over x squared from 1 over y to infinity, and that just equals 1 over 2y, 0 minus negative y, and then f of y equals a half. So this was the first limit. It's not that simple with as it was with f of x. We have to use the second limit there, which is y to infinity, as we saw in the graph in the previous problem I introduced. So that will be y to infinity 1 over 2x squared y dx, which equals 1 over 2y minus 1 over x from y to infinity, which equals 1 over 2y, 0 minus 1 over x. F of y equals 1 over 2y squared when y is greater than or equal to 1. Okay, so just to get an idea of how the graph looks, this will be the graph here. This is the origin. Up till 1, the value is 1/2. After that, it's 1 over 2, 1/2 times 1 over y squared. As you see, slowly decreasing, and then becomes a little bit of a constant there. Okay, so now we have to verify that f of x and f of y are valid density functions, and to do that, we have to show that they're valid if their integrals over the bounds are equal to 1. So yeah, so for f of x, which was ln of x over x squared greater than or equal to 1, the limits is from 1 to infinity ln of x squared dx, of course, which equals negative ln of x plus 1 over x from 1 to infinity 0 minus negative 1, which just equals 1. So we can verify that this is, f of x is a valid density function. For f of y, we have to split it up again. So for the first side, it's from 1/2